Hello everyone, welcome to new class. Today's class is about counters. A digital counter is a set of flip-flops whose states change in response to pulses applied at the input to the counter. As its name implies, a counter is used to count pulses. And a counter can also be used as a frequency divider. That is, a counter can also be used as a frequency divider to obtain waveforms with frequencies that are specific fractions of the clock frequency. And counters may be asynchronous counters or synchronous counters. Asynchronous counters or synchronous counters, and asynchronous counters are also called ripple counters. The ripple counter is the simplest type of counter, and it is easiest to design this ripple counter and requires the least amount of hardware. In ripple counters, the flip-flops within the counter are not made to change the states at exactly the same time. This is because the flip-flops are not triggered simultaneously. These ripple counters are also called serial or series counters. In synchronous counters, these are clocked such that each flip-flop in the counter is triggered at the same time. So here the flip-flop in these counters are triggered at the same time. Whereas in ripple counter, it is not triggered simultaneously. In synchronous counters, the flip-flops are triggered at the same time, and this is accomplished by connecting the clock line to each stage of the counter. And synchronous counters are faster than the asynchronous counters because the propagation delay involved is less. And a counter may be up counter or down counter. So an up counter is a counter which counts in the upward direction, that is 0, 1, 2, 3, etc. up to n. And a down counter is a counter which counts in the downward direction, that is n, n minus 1, etc. 1, 0. Each of the counts of the counter is called state of the counter. So state of a counter means it is the count of the counter, and the number of states through which the counter passes before returning to the starting state is called the modulus of the counter. The number of states through which the counter passes before returning to the starting state is called modulus of the counter. Hence, the modulus of counter is equal to the total number of distinct states or counts. Total number of states or counts, and which include 0 that a counter can store, and the number of input pulses that causes the counter to reset to its initial count is called the modulus of the counter. A 2-bit counter has 4 states. That is, 2-bit counter means there will be 2 flip-flops. So, 4 combinations will be possible. That is 4 states. So, what we can say about the modulus of counter? So, there are 4 states. Modulus means it is equal to the total number of states. So, in 2-bit counter, there are 4 states. So, we can call mod 4 counter. Mod 4 counter. Because there are 4 states and modulus means the total number of states of a counter. So, 2-bit counter is called mod 4 counter, and it requires 2 flip-flops. Similarly, 3-bit counter. 3-bit counter, there are 8 states. That is, 8 means 2 raised, here it is 2 raised to 2, here 2 raised to 3, that is 8 states. So, we can say mod 8 counter. And also, the counter divides the input clock signal frequency. Input clock signal frequency by the number of states. So, in the case of mod 4 counter, the counter divides the input clock signal frequency by 4. Hence, it is called divide by 4 counter. Also, in the case of 3-bit counters, that is mod 8 counter, it divides the input clock frequency by 8. So, it is called divide by 8 counter. And in general, n-bit counter and n-bit counter will have n flip-flops and 2 raised to n states, and divides the input frequency by 2 raised to n. Hence, it is called divide by 2 raised to n counter. So, this is the general case for a counter. That is, for an n-bit counter, it will have n number of flip-flops, 2 raised to n states. Hence, we can call divide by 2 raised to n counter. And mod 2 raised to n. In ripple counters, LSP is the Q output of the flip-flop to which the external clock is applied. LSB is the Q output of flip-flop to which the external clock is applied. And there may be one problem in the case of counters, that is called lockout. And it is the limitation of a circuit stepping into an unwanted state and becoming unable to come out of that state. And this happens in the case of counters. So that counter becomes useless in this case. So a counter whose unused states have this feature is said to suffer from the problem of knockout. That is, because of noise spikes, the counter may find itself in some unused state, and subsequent clock pulses may cause the counter to move from one unused state to another unused state, and the counter may never come to a valid state, and that is called lockout. Next is combination of modulo counters. A single flip-flop is mod 2 counter, and counters of different modes can be combined to get another mod counter. For example, to get mod 10 counter, we can combine mod 2 counter and mod 5 counter. Similarly, to get mod 20 counter, we can combine mod 5 counter and mod 4 counter, like that. Let us study about the asynchronous counters. So in asynchronous counters, the flip-flops are not triggered simultaneously. So here the clock is given at the first flip-flop, and so this is the logic diagram for a 2-bit ripple up counter, and this is using negative edge triggered flip-flop. So here JK flip-flops are used, and JK inputs are set to 1, that is in toggle state. And here the Q output is given to the clock input of the second flip-flop. And as we have already told, the LSB is the Q output of the flip-flop to which the external clock is applied. So these are the two outputs, Q1 and Q2. So which will be the LSB? LSB is the Q output of the flip-flop to which the external clock is applied. So this is LSB and this is MSB. So Q2 and Q1 is the state output, that is Q2, Q1 will be the output. So Q1 is the LSB and Q2 is the MSB. And this is a negative edge triggered flip-flop, and this is up counter. So it counts in the order 0, 1, 2, 3 like that. That is, this is a mod 4 counter. 2-bit means it is mod 4 counter. So there will be 4 states, and that are 0, 0, 0, 1, 1, 0 and 1, 1 are the 4 states. And here, first of all, the counter is initially reset to 0. That means initially reset to 0 means Q1 and Q2 are equal to 0. So initially Q1 equal to 0 and Q2 equal to 0. When the first clock pulse is applied, then the flip-flop 1, that is the first flip-flop, toggles at the negative going edge of the clock pulse. So initially Q1 and Q2 are 0. So up to this is Q1 and Q2, up to this negative edge Q1 and Q2 are 0. So after the first clock pulse, that is at the negative clock edge of the clock pulse, the Q1 changes from low to high, that is this is J and K are both 1 and this flip-flop acts, that is Q1 toggles. Q1 toggles means this is 0 at first, so Q1 changes to 1 and up to the next negative going edge of the clock pulse, it will be high, and Q2. So it will be high up to this next negative going edge of the clock pulse. Q1 will be equal to 1. That is first clock pulse Q1 equal to 1. And what will be Q2? So this is 1 and this is applied to the clock input of the second flip-flop. That means this is a negative edge triggered flip-flop. So a high to this negative edge triggered flip-flop means this flip-flop has no effect or its output will not change. So Q2 will be equal to 0 in the first clock pulse. So it will be 0 up to next negative edge of the clock pulse. So this is 1 and 0. And next, the second, when the second clock pulse is applied, so this is the second clock pulse. So at the negative going edge of the second clock pulse, this flip-flop, first flip-flop again toggles. That means this is 1 in the previous case. So it will toggle mean 1 changes to 0 and it will continue up to the next negative going edge of the clock pulse. That is after the second clock pulse, at the negative going edge of the clock pulse, Q1 toggles. Q1 toggles means it will become 0. Then what will be Q2? This 0 is applied at the clock input of the second flip-flop. So when 0 is applied at the flip-flop 2, then this flip-flop reacts. That is the Q2 will toggle. Q2 toggle means this is 0 now and it will change to 1 up to this negative going edge. That is it will become 1. So Q2 will be equal to 1. And when the third clock pulse is applied, so at the negative going edge of the third clock pulse, Q1 again changes. That is it will become 1. So at the third clock pulse, Q1 becomes 1 and it will continue up to the next negative edge of the clock pulse. So Q1 will be equal to 1 and this 1 is applied at the clock input of the next flip-flop. So it will not react. So Q2 will be equal to the previous state, that is Q2 is equal to 1. That is Q2 is equal to 1 up to the next negative going edge of the clock pulse. Then so after the third clock pulse, Q1 is equal to 1 and Q2 is equal to 1. Then when the fourth clock pulse is applied, Q1 toggles. Q1 toggles means Q1 changes to 0. So Q1 changes to 0 up to the next negative going edge of the clock pulse. And this 0 is applied to the clock input of the next flip-flop. So this flip-flop again toggles, that is Q2 changes, Q2 is 1 in the previous case, so it will become 0. That is Q2 changes to 0 up to the next negative going edge of the clock pulse. So in the first clock pulse, Q2 is the MSB, so we can write 0, 1. So this is the first case. So this is the first clock pulse result. Then next is 1, 0, and this is 1, 1, and this is 0, 0. So 0, 0 is the state of the counter after the fourth clock pulse. So for subsequent clock pulses, the counter goes through the same sequence of states. So it acts as a mode 4 counter. Mode 4 counter with Q1 as the LSB and Q2 as the MSB. So the counting sequence is 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, again 0, 1, like that. Next is 2-bit ripple up counter using positive edge triggered flip-flop. So here this is a positive edge triggered flip-flop. Here the Q1 bar output of the first flip-flop is given to the clock input of the second flip-flop. In negative edge triggered flip-flop, Q1 output is given to the clock input of next flip-flop, whereas in positive edge triggered flip-flop, Q1 bar output of the first flip-flop is applied to the clock input of the next flip-flop. And so this is the logic diagram, and we can draw the timing diagram. So the flip-flop F2, that is the flip-flop 2, toggles whenever Q1 bar changes from 0 to 1, and this first flip-flop toggles at the positive going edge of the clock pulse. So the state transitions occur at the positive going edge of the clock pulses, and here also the counting sequence are like 0, 0, 0, 1, 1, 0, 1, 1, like that. And initially the flip-flop is reset, that is Q1 equal to 0 and Q2 equal to 0. So initial conditions are Q1 equal to 0 and Q2 equal to 0, Q1, and here we have to draw Q1 bar also. So that is high, then Q2 is 0 initially. Then after the first clock pulse, So at the positive going edge of the first clock pulse, Q1 toggles. Q1 toggles means Q1 changes to 1. That is, this is the positive going edge. So Q1 changes to 1 up to the next positive going edge of the clock pulse. So Q1 changes to 1 means Q1 bar. Q1 bar changes to 0 up to the next positive going edge of the clock pulse. So Q1 bar is 0 now, and that is given to the second flip-flop. So it will not act, that is it will not toggle. So Q2 is 0 up to this positive going edge of the clock pulse. Next clock pulse. So Q2 is equal to 0. And after this second clock pulse at the positive going edge, Q1 changes. Q1 changes means it will change to 0 up to the next positive going edge of the clock pulse. So Q1 equal to 0. Q1 0 means Q1 bar is 1. So Q1 bar 1 means, and that is applied to the clock input of second flip-flop. So this is positive edge triggered flip-flop. So Q2 toggles. Q2 toggles means it will change to 1. So Q2 equal to 1 after the second clock pulse. Then after the third clock pulse. After the third clock pulse, at the positive going edge of this third clock pulse, Q1 changes. Q1 changes means it will become 1. That is 1 up to next positive going edge of the clock pulse. So Q1 1 means Q1 bar is 0. Q1 bar 0 means no effect for this flip-flop, that is Q2 is 1 in this case. That is Q2 equal to 1, that is previous case. Then after the fourth clock pulse, Q1 again toggles at the positive going edge, that is it will become 0 up to the next positive going edge of the clock pulse. So Q1 becomes 0. When Q1 becomes 0, Q1 bar is 1. So Q1 bar becomes 1 means the second flip-flop toggles, that is output toggles means Q2 is equal to 0. Q2 is equal to 0 in this case. So up to next positive going edge, Q2 will be equal to 0. So this is the case for this positive going edge triggered 2-bit ripple counter. So here first case is 0 0, next is 0 1, then 1 0, 1 1, then after the fourth clock pulse it will become 0 0 again, that is it will continue like this. So this is about the 2-bit ripple up counter, both using negative edge triggered flip-flop and using positive edge triggered flip-flop. So this is a mode 4 up counter. And thank you for watching the class. If you like the classes, please like, share with your friends and subscribe my channel.